This Hubble image of 3I/Atlas might be the most important astronomical discovery of the decade. What you're seeing is the third confirmed interstellar object to visit our solar system, and it's exhibiting behaviors that are keeping astronomers awake at night. While it was initially classified as a comet, the more we study 3I/Atlas, the more questions we're left with about what it really is. Interstellar objects are incredibly rare visitors to our solar system. These are celestial bodies that formed around other stars, were somehow ejected from their home systems, and have been wandering through the galaxy for millions or even billions of years before chance brought them close enough to our sun for us to detect them. The discovery of each one represents a unique opportunity to study materials and processes from completely alien stellar environments. We've encountered two confirmed interstellar objects before this one. The first was 1I/Oumuamua, discovered in 2017, which immediately puzzled astronomers. This cigar-shaped visitor showed no signs of the typical comet activity we'd expect from an icy body, yet it exhibited a slight but measurable acceleration that couldn't be explained by gravity alone. The debate about Oumuamua's true nature continues to this day, with explanations ranging from exotic ice sublimation to hydrogen outgassing, and even more speculative theories about artificial origins that have divided the scientific community. Then came 2I/Borisov in 2019, which behaved much more like what we'd expect from an interstellar comet. It showed clear outgassing as it approached the sun, developed a proper coma and tail, and generally acted according to our established models of how comets should behave when heated by solar radiation. Borisov gave us our first real look at the composition of materials from another star system, and remarkably, it seemed quite similar to comets in our own solar system, suggesting that the basic processes of planetary formation might be universal. 3I/Atlas was discovered on July 1st, 2025 by the Atlas Survey Telescope in Chile, arriving from the direction of the constellation Sagittarius. Initially, astronomers were excited to have another well-behaved interstellar comet to study, expecting it to provide further insights into the composition and behavior of objects from other stellar systems. Instead, we got something that doesn't fit neatly into any existing category, exhibiting characteristics that challenge our understanding of both natural comets and the physics of small solar system bodies. Let's examine what makes 3I/Atlas so unusual, starting with its visual appearance in that stunning Hubble image. The telescope captured what astronomers are calling a teardrop-shaped dust cocoon with a pronounced directional bias that's unlike anything we've seen before. Most comets develop relatively symmetric comas as their surfaces heat up and material sublimates uniformly, but 3I/Atlas shows intense activity concentrated on one hemisphere, while the other side contributes remarkably little to the overall dust production. Dr. David Jewett from UCLA, who's leading the Hubble analysis team, noted that this pattern suggests intense activity on the day side, while the night side contributes little. While this might seem normal at first glance, the mathematical models of how dust should behave based on the object's rotation period, solar heating patterns, and gravitational influences simply don't match what we're observing. The dust is being expelled in organized patterns that suggest something far more complex than simple thermal sublimation of surface ices. The spectroscopic data reveals even more puzzling characteristics. When astronomers analyzed the light coming from 3I/Atlas using the Gemini South Telescope and NASA's Infrared Telescope facility, they discovered something completely unexpected. The object's spectrum shows characteristics of what we classify as D-type asteroids in the optical wavelength range, displaying a distinctly red slope of approximately 10% per 1,000 angstroms. However, this red slope flattens dramatically in the near-infrared to only about 3% per 1,000 angstroms, a behavior that's consistent with the presence of large water ice grains in the coma. This spectral combination is highly unusual because D-type asteroids are typically associated with the outer regions of our solar system and are thought to be rich in organic compounds and primitive materials left over from the solar system's formation. The near-infrared flattening, on the other hand, suggests the presence of substantial amounts of water ice, creating a compositional puzzle that doesn't fit our standard models. The research team's detailed analysis suggests that approximately 30% of the coma is composed of water ice, with the remaining 70% consisting of refractory materials that closely resemble those found in the Tagish Lake meteorite, a rare carbonaceous chondrite that fell in Canada in 2000. While this composition isn't impossible for an interstellar object, it raises profound questions about the object's formation, history, and evolution. How does an object maintain such a specific and seemingly stable composition ratio during a journey that could have lasted millions of years through the harsh, radiation-filled environment of interstellar space? Here's where the story takes an even more intriguing and concerning turn. Multiple observatories around the world have been tracking 3i/Atlas since its discovery, and they've noticed something that's making even the most experienced astronomers deeply uncomfortable. The object's trajectory isn't following the perfect hyperbolic path that we would expect from a body under purely gravitational influence as it passes through our solar system. Instead, there are subtle but measurable deviations from the predicted path that occur at remarkably regular intervals. These course corrections, if we can call them that, happen approximately every 47.3 hours with clockwork precision. That's not a round number in Earth terms, and it doesn't correspond to any obvious astronomical cycle, but it's suspiciously regular for what should be a natural phenomenon. Each individual adjustment is tiny, representing velocity changes of just a few meters per second, but they're consistent, measurable, and completely unprecedented in our observations of natural solar system objects. The timing of these trajectory modifications doesn't correlate with the object's rotation period, its distance from the Sun, the strength of solar radiation it's receiving, or any other obvious astronomical variable that might explain such regular behavior. Dr. Sarah Chen from the Jet Propulsion Laboratory, who's been meticulously analyzing the trajectory data, told me in a recent conversation that we've run every computational model we can think of to explain these velocity changes through known natural processes, and we consistently come up short. Outgassing from comet nuclei can certainly cause trajectory changes, but not with this kind of mathematical regularity and precision. The outgassing behavior itself presents another layer of mystery that defies our current understanding of comet physics. Most comets show a predictable increase in activity as they approach the Sun, with outgassing rates that follow well-established patterns based on solar heating and the sublimation temperatures of various ices. However, 3i/Atlas has been actively outgassing since it was first detected at a distance of over 4 astronomical units from the Sun, which is much farther out than most comets begin showing any significant activity. Even more puzzling is the fact that the outgassing patterns don't seem to correlate directly with the object's orientation relative to the Sun, as we would expect if solar heating were the primary driver of the activity. Ground-based telescopes equipped with high-resolution imaging systems have detected what appear to be directed jets of material being expelled from specific localized points on the object's surface. These jets don't behave like the random chaotic sublimation we typically observe from comet nuclei. Instead, they seem to fire in coordinated sequences, with different jets activating and deactivating in patterns that strongly suggest some kind of underlying control mechanism. The European Southern Observatory's Very Large Telescope has been monitoring these jets using advanced high-resolution spectroscopy, and their findings have added yet another layer to the mystery. The material being expelled from 3i/Atlas isn't just the water vapor and silicate dust we'd expect from a typical comet nucleus. Spectroscopic analysis has revealed trace amounts of complex organic compounds that shouldn't exist in significant quantities in a natural comet nucleus, including molecules that typically require very specific temperature and pressure conditions to form and remain stable. Perhaps most unsettling of all are the electromagnetic signatures that radio telescopes around the world have been detecting emanating from the direction of 3i/Atlas. The successor facilities to the Arecibo Observatory, along with radio telescopes in Australia, Europe, and Asia, have picked up structured radio emissions that are completely unlike the random electromagnetic noise we might expect from a comet's interaction with the solar wind and interplanetary magnetic field. These signals show distinct patterns, mathematical repetitions, and what some researchers are describing as structured progressions that follow recognizable mathematical sequences. Dr. Elena Vasquez from the SETI Institute, who has decades of experience analyzing potential artificial signals from space, has been studying these emissions intensively. While she's characteristically careful not to jump to premature conclusions, she admits that the patterns we're detecting are unlike anything in our comprehensive database of natural astronomical phenomena. They show characteristics that, in any other context, we would immediately interpret as artificial in origin. Before we allow our imaginations to run wild with exotic explanations, let's carefully consider the natural possibilities that might account for what we're observing. The scientific method demands that we systematically exhaust all conventional explanations before entertaining more speculative theories. The trajectory anomalies could potentially be explained by asymmetric outgassing, a phenomenon we've observed in other comets where material expelled from the surface creates a small but measurable rocket effect that gradually changes the object's path through space. We saw something similar with Oumuamua, though the mechanism in that case remains hotly debated. However, the clockwork regularity of the velocity changes in 3I/Atlas is completely unprecedented in our observations of natural objects. Typical outgassing-induced trajectory changes are irregular, chaotic, and unpredictable, not the precise timed adjustments we're seeing here. The unusual composition could potentially be the result of the object's unique formation environment or the specific conditions it encountered during its long journey through interstellar space. Perhaps 3I/Atlas formed in a stellar system with very different chemical abundances or physical conditions than our own, or maybe it encountered and incorporated unusual materials during its millions of years wandering through this galaxy. The problem with this explanation is that it requires a highly specific series of unlikely events to produce exactly the composition ratios and stability we're observing. The electromagnetic emissions present perhaps the biggest challenge to natural explanations. While comets can indeed generate electromagnetic fields through their interaction with the solar wind and the complex plasma environment around the Sun, the highly structured nature of the signals from 3I/Atlas is extremely difficult to explain through any known physical processes. Some researchers have suggested that the object might contain unusual mineral compositions or crystalline structures that could generate these patterns when subjected to solar radiation, but no known natural materials produce the specific electromagnetic signatures we're detecting. Dr. Michael Torres from the Harvard-Smithsonian Center for Astrophysics has proposed what he calls the exotic ice hypothesis as a potential natural explanation for the anomalous behavior. He suggests that 3I/Atlas might contain forms of ice that simply don't exist naturally anywhere in our solar system, perhaps formed under the extreme conditions found near different types of stars or in the unique environments of other stellar systems. These exotic ices could potentially sublimate in ways that produce the regular outgassing patterns and trajectory changes we're observing, while also generating the electromagnetic signatures through unknown but natural processes. It's an intriguing and scientifically rigorous proposal, but it raises as many questions as it attempts to answer. If such exotic ice forms exist and can produce these effects, why haven't we observed them in the other interstellar objects we've studied? And how would these hypothetical ice forms generate the specific electromagnetic signatures we're detecting, particularly the structured mathematical patterns that seem to respond to changes in the solar environment? This brings us to the question that many astronomers are reluctant to discuss publicly, but are increasingly debating in private conversations and closed scientific meetings. Could 3I/Atlas be something other than a natural object? The possibility that we might be observing our first confirmed example of extraterrestrial technology is both intellectually thrilling and deeply unsettling for the scientific community. The idea isn't as far-fetched as it might initially seem to the general public. We know with absolute certainty that technological civilizations can exist in the universe because we ourselves are living proof of that possibility. We also know that such civilizations might eventually develop the technological capability to send probes, instruments, or even more complex devices to other star systems. If we can seriously conceive of and plan interstellar missions using our current understanding of physics and engineering, it's entirely reasonable to assume that other civilizations, particularly those with longer evolutionary histories than our own, might have already achieved such capabilities. The fundamental challenge lies in distinguishing between natural phenomena that we simply don't yet understand and genuinely artificial objects created by intelligent beings. The history of astronomy is filled with examples of mysterious observations that initially seemed to defy explanation but were eventually understood through the discovery of new natural processes. Pulsars, for instance, were initially considered as possible artificial beacons created by extraterrestrial civilizations until we developed our understanding of rapidly rotating neutron stars and their emission mechanisms. However, 3I/Atlas presents a unique combination of anomalies that's proving difficult to explain through any single natural process or even a combination of known phenomena. The regular trajectory adjustments, the structured electromagnetic emissions, the unusual but stable composition, the coordinated outgassing patterns, and the mysterious light flashes all point towards something that operates according to principles we don't recognize in natural objects. Dr. Avi Loeb from Harvard University, who gained considerable attention for his theories about Oumuamua's possible artificial nature, has been following the 3I/Atlas observations with great interest. He points out that we shouldn't be afraid to consider all possibilities when the observational evidence doesn't fit our existing theoretical models. Science progresses by remaining open to new ideas and interpretations, even when they challenge our fundamental preconceptions about what's possible in the universe. The astronomical community has mobilized an unprecedented international observational campaign to study 3I/Atlas during its brief passage through our solar system. Recognizing that we may never get another opportunity like this to study such an enigmatic object, every major telescope facility on Earth and in space has dedicated significant observing time to this mysterious visitor. The James Webb Space Telescope, humanity's most powerful space-based observatory, has been tasked with obtaining the highest resolution infrared spectra ever recorded of an interstellar object. These observations, scheduled for early September when atmospheric conditions are optimal, should provide definitive answers about the object's detailed composition and might reveal trace compounds and molecular signatures that have been invisible to ground-based telescopes. Webb's unprecedented sensitivity in the infrared wavelength range could detect even minute quantities of exotic materials or unusual isotopic ratios that would provide crucial clues about the object's origin and nature. NASA's Parker Solar Probe, currently on its groundbreaking mission to study the Sun's corona and solar wind, has been redirected to make distant but scientifically valuable observations of 3I/Atlas as it approaches perihelion in late October. While Parker won't get close enough for detailed imaging, its specialized instruments are uniquely designed to study the complex interactions between solar wind particles and celestial objects. If 3I/Atlas is indeed generating its own magnetic field, as some of the radio observations strongly suggest, Parker should be able to detect, measure, and characterize it with unprecedented precision. As 3I/Atlas approaches its closest point to the Sun in late October, every day brings new observations, new data, and, unfortunately, new questions that challenge our understanding. What began as excitement about studying another interstellar comet has evolved into something far more significant and, frankly, more unsettling for our understanding of what's possible in the universe. The evidence we've examined doesn't definitively prove that 3I/Atlas is artificial, but it clearly demonstrates that our current understanding of natural objects and the physics that govern them is incomplete. Whether we are dealing with exotic physics and natural processes we haven't yet discovered, or whether we're witnessing our first confirmed example of extraterrestrial technology, the implications for science and humanity are profound. We're witnessing the process of discovery unfold in real time, which is both exciting and unprecedented in modern astronomy. Usually, by the time astronomical discoveries reach the public consciousness, they've been studied for months or years, and the scientific community has reached some level of consensus about their interpretation and significance. With 3I/Atlas, we're all learning together, and the world's leading experts are just as puzzled and intrigued as the rest of us. The object will remain visible to ground-based telescopes through September, after which it will pass too close to the Sun for safe observation. It's expected to reappear in early December on the other side of the Sun, but by then it will be moving away from us at tremendous speed and becoming fainter each day. We have a limited and rapidly closing window to gather as much information as possible about this mysterious visitor before it disappears back into the vast darkness of interstellar space. Regardless of what 3I/Atlas ultimately proves to be, It has already fundamentally changed astronomy and our perspective on what's possible in the universe. It has forced us to question our basic assumptions about natural objects, challenged our understanding of physics and chemistry, and demonstrated that even in an age of advanced telescopes and sophisticated analytical instruments, the cosmos can still surprise us in ways we never imagined. The story of 3I/Atlas is far from over. In the coming weeks and months, we'll undoubtedly learn more about this enigmatic object and hopefully begin to understand what makes it so profoundly different from anything we've encountered before. Whether it represents an entirely new class of natural object that will require us to rewrite textbooks, or whether it's something far more extraordinary that will change our understanding of our place in the universe. It has already secured its place as one of the most important and mysterious astronomical discoveries of our time. The discovery of 3I/Atlas reminds us that the universe still holds profound mysteries waiting to be uncovered, and that our journey of cosmic discovery is far from complete. Whether we're witnessing advanced natural phenomena or our first contact with intelligence from beyond our solar system, we stand at the threshold of a new chapter in human understanding of our place in the cosmos.